Hello everyone, today we're gonna build another prediction model whether a patient is likely to get stroke based on some input parameters, general information such as gender, age, work type, residence type, and as well as some medical information such as average glucose level, BMI, smoking status, or heart disease. And let's get down to the code line here. I open up my Jupyter notebook and import all the libraries, and next thing I will define my data set pd read underscore csv r, and I think made a mistake. Of course it's not a capable data set I wanted to import. It's the one directory that I need to put here and call from my computer, of course. And yeah, there you go, we got that. And next thing is we want to see the first 5 rows. It's listed as an index, and we can see that there's some object values, probably string, gender, there is smoking status, also object, ever married, work type, ever married, work type, and residency type. These ones need to be maybe label encoded. Maybe for gender, if there's only 2 values here, we may one hot encode this one. But stroke is our main target here. I think it's in integer format. We want to make sure about this one. D types, and we can see that all of these in stroke is integer format, gender again, object, ever married, work type, residence type, and smoking status. We will need to handle all of these, and also want to make sure that there's no null values here. So let's print it out. df.isNull sum, and we only have BMI here as defined as there is over 200 null values in there, so we can handle this one by for simplicity say field missing BMI values with the mean BMI. So let's go ahead and do that. df BMI dot fill NA, again df BMI dot mean, and one in place true. And again, let's find out, there's no null values left, so we handled this one with inserting mean values instead of NAs. So as the next thing, I want to see create some charts to be able to visualize what we have in here. Our main target is again stroke values, so we may go ahead and create a plot, count plot, which is gonna compare the values we have in stroke 1 and 0, 1 4 likely to have stroke, and 0 4 not expected to have. And I want to also put some names on the labels. X for stroke, and also Y label, count, and plt dot show. Here we can visualize, it's not very much pretty looking, but we can see that over around 5,000 patients predicted to be, like, they're having not prediction at all. There is patients not having stroke at all, but stroke having patients around a few hundred range. We can see also have some generic information such as age distribution, and create another chart, histogram chart for this one. sns.hist plot df age again and kd true. Number of pins I want to put 30 and color visualize as blue. I want to name the title of this one and go ahead age distribution for X label. Let me get that from here. It will be much easier to name. Age, of course, and frequency. And we can see the age distribution. Just maybe another thing, I can define the figure size. plt.figure fig size equals to 10 and 6, which is much better. We can see that there is 55 to 60 range of age. People tend to have people in the data set more likely to have this age actually, and some around 80 years of age. One another thing, maybe we can see the BMI distribution, but I want to skip that part and maybe create another age stacked area chart, which will be much better for us to visualize what we have here. Let me get this first line of code snippet here, and down below we can go ahead with the KD plot. This time we want to visualize the stacked area chart, so that we want to segregate the data into whether they have stroke or not, and based on their age. So the F stroke should be equal to this one true, but we also want to have age here and label them as a stroke. I'm also always misspelling stroke here, and shade true, and the color I want this one for red. I want to copy and paste, and instead of 1 let's put 0 this time, no stroke obviously, and make it blue instead. And maybe I need some title and all the others here as well. Better visualize, no harm in visualizing better the age distribution by stroke, outcome, age, and say density. It's going to be area chart, looking very nice. So we can say that easily by stroke outcome there's 80 years of age. Maybe, okay, we did not label here. I'm maybe forgetting something here. PLT legend. I forgot to insert. Yeah, it's much better. So here we got the legend here, stroke, having patients around 80 years of age, but interestingly no stroke. After 50 years of age it's declining. The number of patients, I believe, having less stroke, but instead having more stroke, it's increasing. So it's a really good chart to have. Also we can go ahead and create another one for BMI distribution and visualize this one as well. So instead of age we insert here BMI, pretty much else the same density BMI distribution. So around 30 BMI range, no stroke, as well as stroke increases, but stroke number of patients who had stroke surpass no stroke. It can be clearly seen. Might be a good indicator that BMI around 30 is likely to have more stroke, one another good factor. And I can have more clear charts here, but I want to go ahead with the correlation matrix, which is quite important for us to understand what sort of attributes the parameters have in correlation with another parameters. Let's get again the plt.figure1 and go ahead with the rest of the code here. So df.select underscore d types include equals to float and integer 64. We insert here the formats and then dot correlation. Once we inserted all the formats here, we can create our heat map for annotation true and CMap, as always my favorite cool war, and plt.title, let's call it correlation matrix, and plt.show. We can now clearly visualize these all information. Here age is highly correlating with all these information, all medical information, hypertension, heart disease, average glucose level, BMI, and stroke. And if there is any, there's not many negative correlation. ID is now not in our range at all. It's unique value, so we want to get rid of this one. So we will totally ignore. However, the rest, age and the other information, as we expect, highly correlates. And next one, we can define the features and targets. Define features and targets. So what we want to do, the ID is a unique value, as we mentioned, so we want to get rid of that one as well, and drop also our target value, which is stroke columns equals to ID as well as stroke, and for the Y, our targets to be inserted here. Once we done with this, we will split the data set. Split the data sets with x underscore train, x underscore test, and same for again y train underscore test. We will utilize scikit-learn libraries functionality module to be able to visualize this one. Test underscore size. Our size is going to be 20% of all data set, and random state again as usual 42. Once we set this, we will start with the pre-processing for numerical and categorical values. We will define a pipeline for this. Why we have here pipelines in machine learning in specifically needed for area sequence of pre-processing types. So that can be executed in a specific order, but for this sort of data set we only need single step of pipeline. So let's go ahead with pre-processing, and for numeric features what we have here is age, average glucose level, as well as BMI here, and numeric dot transformer equals to pipeline steps and scalar and standards scalar. Hope that works. Numeric is not defined, so I think maybe this is underscore. Yeah, it works perfectly fine. So this pre-processing from the scikit-learn library that standardizes features by removing the mean and scaling to unit variance. This means for each feature the mean value will be subtracted, and then the feature will be divided by its standard deviation, highly statistical. So this is a common requirement for many machine learning estimators to perform well, because it ensures that each feature contributes to equally to the analysis. So next thing, for the categorical features, I need to define the categorical features first. Let's copy and paste numerical part, and I'll need to change the input variables here. There is gender, hypertension, there is heart disease. This is all we identified when we had a look into the data set initially. So all coming from the actual data set. We need to label, encode the rest of it to be able to work with it when we model our prediction. Residence underscore type, and lastly smoking status. Smoking underscore status will also need to be inserted here, and we will go ahead with the again categorical transformer, which is going to be again pipeline steps. We need to define that as the generic pipeline feature, and go ahead with one hot encoding. Let me put parentheses here, and because we will need to insert one hot encoder and handle underscore score unknown equals to ignore. I think that should be it, but looks like there is a typo here. Closing parenthesis does not match open. Okay, this must be something wrong. Hot scalar. I don't really understand what happened here. Let me check this one. Here we got a okay. So one hot encoder is gonna be handled on ignore, and maybe we forgot another parenthesis here. Yeah, that works perfectly fine. And we will now compute the class weights. It's to handle imbalance. We don't know whether we have imbalance, but it's good to have this step to be able to make sure we are on the correct path. So let's go ahead and put a title here and define the weights. Weights. Oh, that is correctly spelled. Class underscore weights. Class underscore weight dot compute underscore class underscore weight equals to, we will input here balance. Classes is mp dot unique y underscore train, and for y underscore train. We already defined our y train so that we can go ahead and define all these for class weights. And when I define the dictionary, enumerate weights. Hope that works. Class np unique classes. Class weights is not defined. Class weights again, spelling class weight is not defined. Class weights. Okay, that's not looking good at all. We don't know the reason why class weights. Again, typo. Again, a typo. HT class weights HT. Enumerate. Weights. Again, another typo. Here. GHTS. Yes, finally it works. And we will need to define the random forest pipeline for the class weight. Next thing will be RF underscore pipeline. That was pretty annoying. Pipeline preprocessor and preprocessor. So the definition of this dictionary format, okay, shouldn't be dictionary though. Okay, let's jump on to the second parameter, which is gonna be classifier, random forest classifier, and again I have another parenthesis in random state equals to 42, and class underscore GHT, class underscore GHTS. I finally found out the error. I skipped reprocessing parts defining preprocessor with numeric features and categorical features we set. So once I apply this step, we're good to complete that part and go ahead with the hyperparameter tuning. And so the compute class weights also works for us. Next thing was hyperparameter tuning, and we will need to now initialize grid search CV with the pipeline and hyperparameter grid. So let's go ahead with this one. Grid underscore search underscore RF grid search CD RF underscore pipeline grid underscore RF. You need to define up to 5 for this one, and scoring will be in ROC AUC this time. And I want to go ahead with number of jobs -1 to be for our CPU to manage all these in parallel. So the next thing is fitting this grid search into our model. Grid underscore search underscore RF dot fit x underscore train and y underscore train. Hope that works. There's no typo at all here. And typo here, but now corrected and working perfectly fine for grid search, fitting into our model. And we found out that there is the classifier estimator. This is what we set here. Minimum sample split 5 and classifier number estimator, and best score for class weight is 80, which is not quite bad, but we're gonna go ahead with the predicting numbers here, prediction model numbers here, pred underscore RF or y grid underscore search underscore RF dot predict pred x underscore test here, and want to print out the classification report. Print classification report for random forest with class weights and classification underscore report y test and y pred underscore RF. So there you go, we got the numbers here. The precision and recall for non-stroke patients is quite high, and class weight is quite high as well, but with the people who have stroke poorly executed here, it's 6%, 31%, and class weight 11%. We can also go ahead with the ROC AUC score for the number and of course with the class weight numbers, but it's not very much promising looking at this table here. We can go ahead to adjust the threshold, which need additional steps to be able to find out, maybe adjusting our parameters better, and then we can have better results, which might satisfy some of medical setting requirements, because I think recall value is quite important for predicting a person who might have a stroke in the near future. It's, I think, for medical setting quite important. So let's go ahead for threshold step, just threshold markdown. And this time I'm gonna call another module from scikit-learn again, scikit-learn matrix sklearn dot matrix and import, of course, from again import precision underscore recall and curve. And next thing is we want to do probability scores for the positive class and calculate the precision recall and thresholds, which has some more extra steps here. Y scores RF is gonna be grid dot search underscore RF dot predict underscore proba x underscore tests, and we'll need to insert these numbers. Grid is not defined, shouldn't be correct, so maybe underscore is that's correct. And let's go ahead with the precision recall and all the others. Precision recall and threshold we need here, and precision we are now tuning the precision thresholds so that we can tune the recall amount, recall value. Y underscore scores RF, and that works very nice. And desired recall we want to set is equal to 0.8 and closest 0 underscore R is gonna be MP argmin MP dot ABS recall desired underscore recall, and we'll need that once more for P precision, of course, and closest underscore 0 underscore R. And lastly, define selected threshold is gonna be thresholds closest 0 underscore R. Thresholds not defined, thresholds not defined. Okay, maybe we didn't call this one. So thresholds, yeah. Now that one works as well. Now we can print out the threshold numbers here. Print again, for simplicity, selected threshold and selected underscore threshold. And the same for corresponding precision and corresponding selected threshold closest underscore 0 underscore P. completed the adjust threshold here, and we're now able to compare these to the initial model results as well as the lastly adjusted model results. So what we have here, the precision for the class for 1 significantly decreased to 15%, which is not quite good, but we were expecting to increase the recall percentage, which is increased to from 6% to 81%. So the adjusted RF is much better at identifying actual positive cases. And for the F1 score also we got increase from 11% to 26%. Overall accuracy is decreased to 71%, but it's eventually the medical settings appropriateness actually takes place here. The initial RF classifier is very conservative, so favoring precision over recall values. So maybe in a medical setting where missing a stroke can be highly dangerous and could be very problematic. For RF classifier with the adjusted threshold here for this model is much more aggressive in predicting strokes, which is typically more desirable for medical settings, I believe, for such critical conditions. However, on the downside, it's typically having lower precision and leading more false positives, which could increase healthcare costs and patient anxiety, but could be more acceptable if follow-up tests are reliable and affordable. So it depends on the medical setting and the healthcare system's capacity to handle false positives and on the specific costs for financial, emotional, or could be also ethical values associated with these all model and all the negative values here. In a situation where it's crucial to catch as many positive cases as possible, the adjusted RF might be preferred despite its lower precision. I think this would be it for today's video. Thanks very much for watching me today.